started. Okay. So the first speaker of today's session is going to be Madan Rao, comes from NCBS, and he's going to talk us about active matter, for the looks of it. The talk is 25 minutes, and after that, you have 20 minutes for questions, okay?
Yeah, great. Thanks a lot. So I've been thinking about, for a long time, I've been in collaboration with my colleague, Jitu Mayer at NCBS. We've been thinking about the organization of molecules at the cell surface and how they are driven by contractile stresses arising from its proximity to the actomyosin cortex. But over the years, our attention has turned more and more towards the actomyosin cortex, and so that's what I'll be talking about today. I'll be talking about the novel properties exhibited by actin and myosin when they are driven out of equilibrium. And this is largely inspired by work with Jitu Mayer, who's a cell biologist at NCBS, and Thomas Lequi, who works on tissue mechanics at Marseille. So this work was done with Ayan Rai Chaudhary, up there, who's an extremely talented postdoc and who's now looking for jobs. So I would really pitch in for him. He's extremely talented, and a graduate student, Saptarshi Dasgupta, and that's the preprint that, a recent preprint that much of this talk is based on. Okay, so I'll sort of do the customary introduction to active matter as a non-equilibrium driven state of matter, and I'll very quickly talk about what this entails for non-equilibrium forces and fluxes, and briefly talk about non-reciprocity. And then I'll jump into what we call non-equilibrium force patterning, which is a consequence of the activity of the cytoskeleton. And I'll be talking about force patterning and the emergence of singular lines, which for the biologists will be stress fibers, which arise in the steady state of these actomyosin cytoskeleton. I'll also describe mechanical fragility and excitability that is exhibited by this system. So please do stop me if there are some burning questions, else I'll just continue and we can have the question session later. So this is the customary slide about active matter. It's a non-equilibrium driven state of matter. Many examples of this in living systems and in synthetic analogs, and they're listed here. The defining feature of active matter is that each constituent is associated with an internal chemical cycle, which is maintained far from equilibrium and thereby sustains a steady current. Therefore, at the scale of each particle, this carries a dissipative times arrow. And as a consequence, the steady state distribution of a collection of active particles is not time reversal invariant and indeed can carry a current. That is its non-Boltzmann. There's a paper which explicitly demonstrates this in the context of two active particles embedded in a fluid, and that's not given here. And yeah, so that's my customary slide on active matter, and this is what we are going to do now. What we'll study is the actomyosin cytoskeleton, which resides within the cell. So the interior of cells, or that's shown here, or suitable in vitro reconstitutions, in vitro systems, such as shown here, namely cells embedded in a micro-patterned, attached to a micro-patterned substrate. They provide a unique opportunity to study the rheology of active renewable matter. I'll define what this active renewable matter is. And what it exhibits as a consequence is a system spanning actomyosin force chains that you see here as these bright lines. Okay? And these force chains emerge as a result of active contractility coming from actomyosin and turnover. This is what I meant by renewability. That is, myosin binds and unbinds from the actin meshwork. Okay? And moreover, these stress fibers or these lines that you see are held together by boundary anchoring from proteins such as integrin and focal adhesions. Okay, so this is a confined actomyosin cytoskeleton embedded in the cell. It's active in the sense it uses ATP to generate local contractile stresses. It's also renewable, namely myosin binds and unbinds. Okay, so this is the system that I like to look at, and what you see here is that this what we'll sort of discuss is that this confined active cytoskeleton is a novel system that exhibits interesting material properties which spans the limit of material stability. And in other words, it exhibits what's called material fragility, and a sort of characteristic of this material fragility is the stabilization of these tension force chains that I alluded to earlier. I'll also discuss the normal segregation dynamics that arises naturally in these systems, and the coexistence with excitability as shown here on the right side. You see these excitable waves of actomyosin which are seen in these osteoblasts which are attached to a hard substrate. Okay, so these are the sort of ingredients of the actomyosin cytoskeleton that you need to take away. The actomyosin cytoskeleton is a meshwork which is elastic because of cross-linkers, and it's active because of these bound myosin minifilaments. So bound myosin minifilaments bind to the, myosin minifilaments bind to this actin meshwork. Locally, they apply active stresses, and as a result of these large stresses that are applied, they unbind. Okay? So there's a binding, unbinding, or there's a turnover of myosin minifilaments, which depends on the local strain that is applied at the meshwork. Okay? While it's bound, it applies a whole lot of different kinds of stresses onto the actin meshwork, and that's listed here on the right-hand side. It could apply both compression and shear. Okay, so these the actomyosin meshwork indeed acts as both as force generators, that is, they locally drive contractile stresses, but because this turnover is dependent on the local stress or the local strain, they also act as force sensors. So it's this dual role of force generators and force sensors that gives rise to the interesting properties that I'm going to talk to you about. Okay, so let's sort of start with a thought experiment where you start off with a meshwork, as shown here. We'll start off with an isotropic actin meshwork, and at time t equals 0, we'll sprinkle myosin, ATP, and we'll ask what happens. And the idea is that we want to arrive at a situation. So for instance, I could either do this experiment with a single species of myosin or 2 species of myosin. Let me use the language of 2 species of myosin because it's sort of easier to tell the story. But what I'm going to describe also holds for a single myosin species. Okay? So imagine I have myosin 1, myosin 2, which I sprinkle on this isotropic meshwork, turn on ATP, and the idea is, does it give rise to structures just shown on the right? That is, dense lines of actin on which reside these myosin 1 and myosin 2. We will take myosin 1 to be more contractile than myosin 2, and so therefore you see these bands of actin have embedded on them myosin 1 more. They're enriched more in myosin 1 than in myosin 2. So myosin 1 and myosin 2 are going to apply differential contractile stresses on this actin meshwork. But because they also bind and unbind in a stress or strain-dependent manner, they will also have differential turnover. That is, one is more sensitive to the unbinding kinetics of myosin 1, for instance, is more sensitive to local stresses than myosin 2. Okay. Indeed, this is not a thought experiment, and there's beautiful recent work by Manuel Theri's group, where you see on the bottom down here, cells which are attached to a micro-patterned triangular substrate, held together at these corners by focal adhesions. And what you see that in the absence of myosin contractility achieved by putting in a drug called blebistatin, you see a sort of uniform meshwork of actin. But as soon as you wash off this drug and restore myosin contractility, you find the emergence of these stress fibers or these singular lines that I talked to you about. Okay? And so this is the, oops, wow. This suddenly disappeared. Oh yeah, okay. Yeah, okay. And so this is the dynamics that I'd like to describe to you. Okay, how do you start from a uniform isotropic actin meshwork to give rise to these singular lines? Okay, and so the description is going to be of the confined actomyosin as an active elastomer embedded in a fluid cytosol. And being an elastomer, it's an elastomer because there's a lot of cross-linkers, which gives it elasticity. Being an elastomer, you can describe it by a strain from an unstrained passive configuration. Okay, so the reference configuration of the actin is without any myosin, is unstrained. As soon as I put myosin, there's a local strain that is generated, and I'll describe that by epsilon ij. Okay, you'll also describe the hydrodynamic equations in terms of an actin density and a fabric tensor Q. The fabric tensor Q describes the microscopic configurations of actin on top of this meshwork. Okay, so that's if you bunch actin in one region compared to the other, this information will be carried by the fabric tensor Q. Okay, the actin dynamics is going to be assumed to be fast, and therefore is going to be slaved to the strain, and that's the equation here on the right. In addition to the dynamics of actin, given by the dynamics of the local strain and local density and fabric tensor, you'll have the dynamics of myosin. And the myosin, we'll consider two species of myosin, myosin 1 and myosin 2. Let's say myosin 1 is more contractile than myosin 2. And we'll have to write down dynamical equations for myosin 1 and myosin 2. Okay? So the dynamical equations that we're going to write down are first force balance and, yeah, sorry. Oh, what happened? Yeah, you think it's a loose contact or something? I don't know, okay. Okay, that's okay, it works now. Okay, so the dynamical equations will be the dynamics of the actin meshwork, and which is given by force and torque balance described here. The local mesh velocity, u dot, is described by forces which are written as the divergence of stresses. The stresses are a combination of the elastic stress, the active stress, and the dissipative stress. Okay? The active stress, as I mentioned before, are functions of the local myosin concentrations. Okay. The dynamics of the myosin is going to be advection by the meshes, which is the left-hand side. And on the right-hand side, you have a diffusion term and a turnover. The turnover, as I said, had a binding and unbinding, and the unbinding term is taken to be strain dependent. Okay, so this is the simple dynamical equations. The strain dependence of the unbinding is taken to be this exponential hill form. Remember, myosin tries to because of contractility, myosin tries to compress the local mesh. Therefore, it drives epsilon or the strain to be negative. Therefore, alpha is going to be, alpha greater than 0 will describe catch bonds, alpha less than 0 will describe slip bonds. Okay? And myosin most often has a catch bond behavior. Okay, so that's clear. The force and torque balance to describe actin dynamics, mass balance equations to describe myosin, the two species of myosin, and the turnover of myosin is given by a strain-dependent unbinding. Okay, so that's the dynamics. Okay, and now we'll start off. We'll try to solve these equations. I'll have to first, before solving these equations, I'll have to tell you what the form of the elastic stresses and the form of the active stresses. And so this is what we take it to be. The elastic stress is taken to be a linear elastic meshwork with a bulk modulus B and a shear modulus mu. Okay. The active stresses are taken to be functions of the myosin densities, ρ1 and ρ2, and also the actin variables, namely its density and the fabric tensor, which, as I said, is slaved to the local strain. Right. So at the moment, I'm just going to take an unbounded system. At the moment, there's an unbounded system, but then later on, I'll tell you the appropriate boundary conditions for. Right. We could. We haven't done that here, but yes, indeed, we could. Yeah. We'll have to write a separate equation for these markers, which are. So the question now is if these markers are bound to actin or not, and they would then have different equations. Yeah. But you could label myosin and actin, and so you can actually see the deformation. Yeah. Okay. So there's a combination of these elastic stresses and active stresses.
Excuse me. Could you tell us what is catch and slip bonds?
Sorry?
Catch and slip bonds.
Right.
What is it?
Right. So, for instance, myosin 2, which is a species of myosin, when it's bound to actin, you could apply a tension to it. You could pull it, and what happens is that it binds more to actin. So people have measured the unbinding rate of myosin as a function of the applied force, and the unbinding decreases. The unbinding rate decreases as you apply force. It only works up to some force. Beyond a certain force, of course, it comes off, right? Absolutely, yeah. Okay, so now the idea would be to unpack this active stresses that I described here, and then see how it affects the equation of motion that I wrote down there. Okay, and what we find is that by unpacking the form of this and using the slaving relations for the actin variables, this leads to a renormalization of the active stresses in the following form, shown here. Now, there are three interesting features that I'd like to highlight about this renormalization. One is that it gives rise to an active pre-stress, namely in the absence of any applied strain, there is, in the absence of any applied forces, there is a pre-stress that is generated by the activity. That's sigma 0, and that's a function of the myosin densities. It gives rise to a renormalized elastic constant here. So you can see that we started off with a linear elasticity, namely sigma, the stress was proportional to the strain epsilon within a bare elastic constant B0. But now the elastic constant gets renormalized, and I'll tell you the form of renormalization. It also gives rise to stabilizing nonlinear elastic moduli shown here. Okay. So indeed, what started off as being a linear elastic material becomes a new nonlinear effective material due to activity. Okay, that's the consequence of activity. And that's reflected here in the energy landscape that you can derive from this, stress-strain relationship. Initially, because it was linear elasticity theory, you had only one minima at a non-zero, at zero strain. But now, because of activity, you see there are actually 4 minima that which I haven't, in this particular case, I'm showing you 2 minima. But let's say there are multiple minima which are generated as a consequence of activity. Okay, so now I'll tell you the promised renormalization. It's easier to see this in variables, not rho 1 and rho 2, which are the densities of the 2 myosin species, but in the segregation parameter phi and the density rho. Okay, and here is the renormalization of the active pre-stress, and here is the renormalization of the linear elastic modulus. You can see that is driven. It can be driven to 0 or negative values depending on the local values of rho and phi, namely the mean density and the segregation parameter phi. Okay?
Excuse me? Yes.
Yeah.
On your slide before, you have a parameter B2. What's the sign of B2?
Right, so B2 is negative, turns out.
Always?
Yeah. It's, B2 and B3, all these terms depend on the local density of myosin. And so it can, by increasing the density, you can drive it, you can change its sign. Okay, I'll skip this contact of time. Okay, so now that was a quick tour to show you that the elastic properties of this material are very, very strange because, for instance, it gets driven to have negative linear elastic moduli. But remember, the system is stable because of the nonlinear stabilization terms. But what we'll do now is to take these equations that I showed here, and do a linear stability analysis about the homogeneous phase. Okay, and what one gets is an unusual segregation behavior. Now, what we find is that starting off from a uniform distribution of myosin, there's a linear instability which drives it to be segregated, gives you the conventional bicontinuous phases of rho 1 myosin density of one species and rho 2, okay, a typical spinodal decomposition. But this happens in the absence of any attractive forces between myosin. So it's purely driven by the myosins coupling to each other via the meshwork, via the elastic meshwork. Okay? And this is a purely an active phenomenon, very akin to, for instance, the MIPS, the motility-induced phase separation, which also happens in the absence of any attractive forces. Okay, so here now is the linear stability phase diagram plotted in the relative contractility between the two species and the relative unbinding rates of the two species. And I just want to show this to show you that there is a large regime in parameter space shown by these yellow regions where there is a spontaneous segregation of the homogeneous, about the homogeneous phase, okay? Giving you a typical spinodal like dispersion, and it gives rise to, for instance, these kind of segregated, conventional segregated patches that I showed you. This is a consequence of the linear instability, of the linear analysis. You can obviously ask questions like, what is the effect of nonlinearities? And that's an interesting story that I'm going to tell you about now. Okay, so now so now the linear stability analysis tells you that you get these bicontinuous, conventional bicontinuous phases of one species, rho 1, segregated from rho 2. We now turn on activity. Since rho 1 was taken to be the more contractile of the two species, the contractility in this region, in this brown region, is higher than the contractility in the blue region. And it turns out that as a consequence, after the linear instability of forming these bicontinuous phases, the enhanced contractility or the differential contractility between the rho 1 and rho 2 makes these bicontinuous phases actually shrink. Okay, so it shrinks here, and the analysis shows you that it shrinks to form these lines. Okay, because as I said, there's a differential contractility within this patch here compared to the outside. This gives rise to a shrinking so it's initially expanding because it forms this, it undergoes a segregation, but when nonlinearities come in, this whole thing shrinks, okay, to give rise to this singular lines. the picture that you should take with you is that these lines are actually high density lines of actin on which myosin is attached to it. Okay? And on the outside of these lines, you have a lower density of actin. Okay? Okay. In fact, what happens is that these lines form and give rise to what's called a finite time singularity. The equations tell you, analysis of the equations tell you that in this region, in this region shown here, the segregation order parameter and the strains diverge at a finite time t0, and they have this following scaling behavior. Okay? This can be derived from the equations, as I said, and shown by numerical simulations of the equations that I talked about. This is a scaling plot which verifies the scaling plot for the segregation order parameter and strain as a function of lateral distance, and that shows the scaling collapse here shows the verification of these scaling forms. Okay? So the bottom line is that these lines, which were the bottom line is that there's a linear instability of the homogeneous phase coming from the interaction of the two contractile species with the elastic meshwork. This bicontinuous phase, because of nonlinearities, starts shrinking into lines. Okay? Yeah.
Necessary to have two types of myosins to obtain these stress bundles?
That's right. So you could even do this with a single species of myosin, and then the segregation is like a liquid gas segregation, where you have a high density bunching of actin and myosin, and there's a low density phase outside.
So to get the time scale of the singularity, do you need to put in like fluid hydrodynamics and some viscous?
So here we haven't put in fluid hydrodynamics.
You have?
We have not.
You have not?
Right,
okay.
Right. We just have the hydrodynamics. So the dissipation is mainly in terms of viscous dissipation in the meshwork.
Okay, and that should dominate over any?
Right.
Well,
Yeah.
okay.
Yeah.
So why do you get lines and not a spherical object?
Right. That's a great question. So that has. Yeah. Okay. So indeed, there are different regimes. So we've done an analysis of this patch. Okay. So this is the high density patch of the actomyosin, and outside here is the low density patch. And this, whether you form lines or whether you form blob, depends on the normal and the tangential forces. And if the normal forces are higher than the tangential forces, then you first get lines, and then this line, over a longer time scale, the lines shrink to form points. Right. Now, what we can do is derive conditions when the normal forces are larger than the tangential forces, and this is what. But that brings us to an interesting question. All this analysis was done for an unbounded system, right? And the idea now is to take this system and then confine it within the walls of the cell, okay? And an interesting feature of stress fibers in cells is the following, that if stress fibers are typically formed when cells are adhered onto a substrate. And when they're de-adhered, you lose the stress fibers, okay? When cells are adhered onto a substrate, focal adhesions hold the cell attached to the substrate, and then these are the sources of these lines. Okay? And this has been shown again by very nice work by Manuel Thierry recently. And when we put in these appropriate boundary conditions, then you find you can stabilize these lines. Okay? And this is what I'm talking about here. You can stabilize these lines, and they form a whole lot of interesting networks depending on the geometries of the stabilization. Okay? You can derive the active versions of Young-Dupré equations at these junctions and at these focal adhesions sites. Okay? And it turns out that what happens here is that this geometry of the meshwork that of the stabilized meshwork is extremely sensitive to the realization of these boundary anchors. The moment you change the boundary anchors, the whole thing will reconfigure to form a new force chain web. Okay? So in this sense, the system is very fragile. Okay? Any slight change on the boundary gives rise to a reconfiguration of the filaments. Okay. I'll now very quickly, I do have time, don't I? Yeah. Yeah. So, okay. So I'll just very quickly, you had a question? Yeah. Yeah.
So one quick thing. So one mode of contractility just comes from the fact that these are elastic polymers that can buckle.
Yeah.
Do you have that in the kind of equations you've written down?
So, okay, so this is a theory on strain. And so remember I said that the effect of contractility is to generate nonlinear terms in the strain. So in some sense, the nonlinear elasticity hides in it things like buckling and sliding. Yeah, but you're right. These things come because of that. So if I were to do a theory of filaments, then I would have to include these things. Okay, now very quickly, I promised that I would tell you something about excitability, or the coexistence of excitability with the emergence of these stress fibers. And that's actually seen best by looking at the linear stability analysis that I talked to you about earlier. What I'm just showing you here is a dynamical matrix which connects the time derivative of the degrees of freedom, the displacement, the mean density of myosin, and oops. Okay, the mean density of myosin and the segregation parameter phi. And this here is a dynamical matrix. The dynamical matrix turns out to be non-Hermitian because of the existence of terms that violate time reversal symmetry. And one consequence of that is the eigenvectors of this matrix need not be orthogonal. And indeed, as you change the parameters describing the dynamics that are there in the dynamical equations, these eigenvectors, which tell you how perturbations propagate, they can actually coalesce. Okay, and so these points are called exceptional points, and these exceptional points are typically found to be gateways to excitability. And I'll just show you here. Indeed, you find traveling waves and swap phases in the phase diagram, and I'll just play the movie which shows that. Oops. Okay. Okay, there was a movie here which tells you, which shows the existence of these traveling wave solutions, which has a speed which is given by the relative unbinding of the two myosin species and their relative contractility, and indeed, it's possible that the excitable phenomena or behavior that I'm showing you at the bottom right here has something to do with these mechanically excitable traveling waves. Okay, so now to summarize, I hope I've convinced you that the actomyosin renewable cytoskeleton is indeed a novel system in terms of its material properties, in terms of segregation and patterning and excitability, and these phenomena seem to coexist. It exhibits a fragile state which is held together by active tension chains, very akin to its dual, namely granular systems which show fragile behavior because of compression chains. Okay? These actin tension chains are stabilized by focal adhesions sitting at the boundaries, and these tension chains may coexist with excitability, as I showed you towards the end. So with that, I'll end my talk and acknowledge the people who did the work. Ayan Rai Chaudhary, as I said, a fantastic postdoc, and Saptarshi Dasgupta, a graduate student in our group. And this also sort of was inspired by earlier work done in collaboration with Thomas Lequi by my ex-student Deb Shankar Banerjee, who is now moving to Chicago, and thanks to the funding given by these organizations. Thank you.
Thank you very much, Madan. There were already some questions, more questions. Students first, students first. Students and postdocs.
Thank you. Very nice talk. So you have two types of myosins,
Yeah.
and that leads you to spatial heterogeneities.
Yeah.
But you said there is no space in your equation, so I'm confused.
Sorry, I can.
Is there space in your equations that you said there was no space?
No, there is
But
space.
there
Sorry,
is?
sorry, yeah. Yeah, I can. Yeah, so there's an advection term, there's diffusion, and there are local stresses, which depend on space and time. Sorry, yeah.
Any other questions?
And as I said, the theory works for even a single myosin species. The segregation is between a myosin-rich region and myosin-poor region.
More questions from students and postdocs preferentially?
Liz.
I think there's somebody.
Thanks for the talk. Here I see elastic stress and dissipative stress. I guess they both together describe some viscoelastic behavior.
Right.
Is it possible to describe viscoelastic behavior which has power law correlations with
Right.
this model?
So in this model, you don't get viscoelastic behavior with power law correlations. But if we allow for myosin to turn over, for actin to turn over, then you get into a strange phase where the actin meshwork is very frayed. You know, it's torn apart, and it might. I mean, we're trying to see whether in that regime where the actin is very frayed, that might be a regime to look for power law correlations. But we haven't done that as yet. Yeah.
Thank you.
Yeah.
A small question. You said that the filamentous structure of the system was because normal forces were higher than tangential forces. What would happen if it was the opposite? If
Right.
the normal forces were weak?
Then it would form these, as you're saying, it would form these blobs. You know?
Okay, like.
Yeah.
Okay, like.
Yeah.
Agglutinose.
Yeah. So in fact, in 3 dimensions, it's interesting that if you do this, you could stabilize sheets first, I mean, and then lines and this thing. Yeah. But again, for my predictions to work, they need to be anchored at the boundaries. This is crucial. Right. So to get stable lines or sheets, you need to be anchored at the boundary. So,
Yeah, thank you. Do your equations allow also the study of spatial covariances, the correlation functions?
Could we compute correlation functions from this? Yes, indeed, we could. Yeah.
And
haven't done that yet, but.
But do you know something about the correlation behavior, the decay, or?
Of course, when the elastic moduli are positive, in the regime where the elastic moduli are positive, you would get the normal solid-like. It's a standard elastic theory, so you'd get the correlations of a standard.
But do you get like also possibility of studying curvature of this?
Of what? Sorry.
Curvature, like metric properties.
So this it's in let's say in 2 dimensions, it's just in a flat geometry.
But in principle, these equations would allow a kind of fluctuations also in other directions.
Yeah. So right. So indeed, you can ask whether you can take these equations and do a plate theory, for instance, right? You could put it on the curved geometry and then write down a strain, which is a combination of the 2D strain and the height degrees of freedom. And this gives rise to traveling waves too. We have done this work. It gives rise to traveling waves which correspond to, a traveling wave of the deformation of this height. You see, here there was a traveling wave of the density of myosin and the strain. When you write a plate theory for this, you find that this traveling wave in terms of the strain and the density field also gets translated to a traveling wave in the shape of that. So you see a the shape which moves with a certain velocity. And this indeed has been seen in experiments in Thomas Lekvy's group in the context of tissue mechanics. And it's called posterior mid-gut invagination. And we're working with him to try to describe this phenomena. Yeah.
So if you had like a gel like this,
Yeah.
and you came in with some little probe that locally would bind strongly to myosin, would you kind of crystallize like sort of these lines coming off of it after a while?
Say it again?
Well, if I came in with something that
Yeah.
myosin like to bind,
Right.
say the myosin 1 would ever like to bind to,
Yeah.
would that after a while sort of nucleate sort of these stress lines from it, do you think?
Oh.
I mean, could you control it somehow? I'm just trying to think, and
Yeah,
then
yeah,
what would that do kind of to the shape of the gel?
I don't know. So you're saying that it's like pinching. You're locally pinching the actin.
Except that you wouldn't pinch it. I mean, you could pinch it, but
Right.
but I guess the myosin would like to bind, and then that sort
Yeah.
of becomes
So-
a preferred
so-
anchoring point.
Right. So what would happen is that locally let's say you locally compress the region, right? And because the actin is now compressed, you'll get more myosin binding on.
Okay, so it's just enough to poke it.
Yeah.
And then you would.
Yeah.
Just wondering if that's a useful thing, or just to think about, like, if a cell comes in contact with something, then that's where the lines would go.
Right. An experiment which I think would be interesting to do is to do a similar thing, but not with myosin, but with these boundary anchoring things. That is, you come from the outside and locally trigger integrin. And integrin will then, nucleate actin and myosin through a signaling mechanism, and then you could see the propagation of the actin myosin. And that would be an interesting thing to work. Indeed, we could actually work on the dynamics with this framework. We could work on the dynamics of that of this. Yeah.
Okay, thanks for the nice talk. I have two fast questions. The first one is related to the Christian's question. Is if you want to compute correlations, you need to put noise in your.
Yes.
And you have idea how to do that?
Have we done that? No, we haven't done that.
No, but you know how to do.
Yes,
Okay.
Absolutely. Yeah.
Because it's out of equilibrium. So you have to put something which doesn't.
Then you'll have to put colored noise or something. Yeah, you could put colored noise in the myosin. Yeah. Yeah.
Second question was somehow in general, are there response experiments like perturbation? I don't know, maybe moving the anchoring points or something.
Not in a quantitative way that you'd like to do. I mean, the experiment that, as I just described, would be to come. So what people have done is to try to trigger integrin activity using forces. So they come with a bead or with which has some extracellular matrix polymers, and they come towards an integrin cluster, and they can ask what happens to the actin and myosin. But it would be good to do these experiments in a controlled manner. Yeah.
So could you, on the other side.
Oh, sorry.
So could you comment on the necessity to have these two different types of myosins? You emphasized the differential contractility.
Right.
What would you get if you would have one myosin?
Right, exactly. That's what so I just for pedagogical reasons or ease to for the explaining, I just use two different myosin species. But the theory works for of course one myosin species, and there you get segregation between a myosin-rich region and myosin-poor region.
Exactly.
So
you also get these stress lines there, right?
Yeah. So you get, and this would be the stress fibers.
Yes.
But indeed, the cell has many different kinds of myosin. And you could legitimately ask this question, and people have started doing experiments on the relative localization of the myosin species and so on.
One minute question.
So there are other phases that one can observe in systems like this, and you have done some work, Aster-like phases and spirals and other things. So you don't see any other mode of contractility in what you have right now. You only see these bundles. Is there a reason why?
So remember, this one is elastic theory in where where you get asters and so on and so forth is when you're treating the actomyosin as a fluid. And so here there are cross-linkers which prevent that aster-like things from happening.
Okay. Let's thank Madan again.
Yeah, thank you.